My name is Stefan, and I work on the Scala team now, and I used to be the creator of Slick. Oh, by the way, don't forget to rate the session. That's why they had me put the slide here. So I'm the original creator of Slick, or Scala Query as it was called, and nowadays I spend most of my time working on the Scala team. So I'm doing a talk in the intersection of Slick and Scala. So we're going to look at implementation details of Slick, but the technique I'm going to show is plain Scala stuff. So you don't need any Slick knowledge to follow this. Maybe a show of hands. How many of you have used Slick? Okay, that's most, but not all of you. So for those who don't know what it is, Slick is the database library that we built at Lightbend. It's for relational databases, and you write your database query in Scala like you're using Scala collections. So this val_q here is a database query. We have a users table, and we filter by ID less than 42 and map to just the first name of the user. And then you run this on a database. You just say db.run and your query. And of course, the whole thing is statically typed. So this result is actually of the type future of vector of string. So the way this works in Slick is that you write the query in Slick's lifted embedding Scala DSL. We used to call it lifted embedding for a few years, mostly because we also had a direct embedding, which we now removed. So it's just called the Scala API these days. But for the topic of this talk, we'll call it the lifted embedding. And this is just plain Scala code. There are no macros, no pre-processing magic or anything. Actually, there are a few macros in Slick, but they're just syntactic sugar, basically. You don't really need them for anything, and we're going to do without them today. So the lifted embedding that you write your code in then builds a Slick AST. So we don't have an interpreter or anything attached directly to this embedding. Instead, we first build an AST from the code that you write, which is not a Scala AST, it's a Slick AST that we define ourselves. And this reifies the computations. So it just captures everything that you wrote in your query as close to the original query as possible. And this AST is then compiled to an SQL statement, a database-specific one. And the statement gets executed on a database, usually via JDBC, and then your results are delivered asynchronously as a future or a reactive stream. What we're going to use today, though, is Toy Slick, which I created by starting with the real current Slick master branch and removing everything that's not really needed. So it cannot execute any queries. There is no query compiler in there. We can compile queries. The AST is untyped. Usually the real Slick AST captures some type information. We don't need that. There are no database-specific profiles. There are only very few operations. There are no option types. That's a very big change, because option types hugely complicate the Slick lifted embedding and the Slick compiler. So we'll just leave them out to keep things simple. There are no type constructors for queries, so everything collection valued is just called a seek. And there are no shape levels, in case you've seen them in the Slick internal. Sometimes they pop up in error messages. We don't need them either. So all we're still going to do in Toy Slick is to take a simplified lifted embedding and build a simplified AST from that. So let's start with the AST, the abstract syntax tree. These are the operations that we need. We have a basic trait node as a supertype for all AST nodes. And then we have a literal node, which contains a literal value of whatever type that you put into the AST, like the number 42 in the example that we saw. And we have a product node, which represents a product or tuple of individual expressions. So all the nodes are expressions here. There are no non-expression nodes in our simplified AST. The product node is a product or tuple of expressions. We have a table node, which represents a basic database table, which is a collection value thing. And for operations, we have map and filter. They act on queries. The way these are implemented is that you get a symbol, which in the case of toy slick is just a wrapper for a name. There's nothing else in it. So you have a symbol and whatever it starts with, the source of the computation, and then a select or where node in there, which uses the symbol. So we have no separate representation for lambdas. They are just integrated into the map and filter node. You'll see that in an example shortly. And in order to refer to these symbols, we need a ref node, which just references a symbol. And we also have a select operation. That's like when you have an expression a dot b, this would be a select of field b in a ref of a. That's how you encode arbitrary paths in the query language. And finally, we have an apply operation, which is used for all kinds of function application or operators, like the less than operator that we saw. That's implemented as an apply, and which operator to apply, in this case the less than, is again encoded in a symbol. And it just takes a number of child nodes, which are the arguments. So that's all for the AST. Here's an example. Again, users.filter and then a .map. So the last thing that happens is a map. So we start with that. And the map has a symbol. You see that here it's from S2. That's the symbol that we generated. So the select expression uses this symbol in a ref. So we say the lambda is basically in the select clause down here is basically S2 to S2 dot first. We don't know that it was originally called U because we do not see those names. They are lost. There's no way that Scala gives us access to these original variable names without using macros or similar techniques. So we have to generate new names. And then in the from clause of this map, we have a filter operation, which looks similar. We have a symbol S1, and we have a where clause, which encodes this S1.id less than 42. And the from clause of the filter operation is the table users. So now that we've seen the AST, which is as simple as I could make it for Toy Slick, let's look at lifted embedding. So what does that mean, lifted embedding? Well, an embedding means that a query language is embedded in Scala, so it's an internal DSL. We're using a Scala library, basically, to embed another language, the query language in Scala. And lifted refers to the fact that any type T is lifted into a type rep of T. So whenever you think you see an int or a string in the query, it's actually a rep of int or a rep of string. So that already takes care of half of the title of this talk. We'll get to the other half later. So let's look at the lifted representation, this rep of T. So here's the simplified version. We need a basic operation to node because we want to build an AST from the lifted embedding. So we have toNode, which gives us the AST representing this rep. And then we have another operation, which is encodeRef, which takes a path. It's called path here. It's a node. It represents a path, and we want this rep to stand for that path. So the invariant here is that after you call encodeRef on a path, it gives you a new rep of T, and when you call toNode on that, you get the original path back. You've seen that in the previous example, like this S2 to S2 dot first. Whatever the object, the rep in there was, we need to tell it now you're S2, because we want this S2 dot first to come out when we call toAST on the right-hand side of the of the filter condition. So we need to be able to encode something into the rep. And down there in the object, we have a way to create a very simple rep of T, where we just pass the node directly in. That's the intrinsic node of the AST. And as soon as you call encodeRef, this node is dropped, and instead when you called toNode, you get out whatever you put in before. This works for all primitive types. So this encode ref here, it returns a rep of t. What we really mean is something more elaborate like this. So we want to be able to return some type R, which is a subtype of rep of t and R. But this would make the types much more complicated, and probably type inference would fail for this if we tried it. But we have different ways to enforce this invariant. So for now, it's enough to know that we have to encode into something that's like the original type. For all primitive types, it's enough to have a rep of t. For other types, we'll see that we need subtypes, and we'll also see how we enforce this later. So let's start with primitive values, the simplest case. We have a literal rep, which takes a value of some arbitrary type t, as long as we have a typed type for t. And this literal rep, of course, extends rep of t. The toNode builds a literal node, as you might expect, and encode ref doesn't have to build another literal rep, it just builds a rep of the new node, because having a rep is enough in this case. So what does this typed type mean, and why is it called typed type? Is it doubly typed? Well, the real Slick has a class called type, which represents a type in Slick's type system. So that's different from a Scala type. And then a subtype of this type is typed type of t, which is also a Scala type. So we carry the Scala type in the Slick type. This allows us to use this typed type as a context bound here. So we can say we want any t that has a typed type, and those are exactly the types that can be used in individual columns as primitive types. In our toy Slick, this is Boolean, int, and string. And we want to be able to call methods on these rep values. You've seen something like _.id less than 42. That's the less than is usually available on int. We want it to be available on rep of int, so we have extension methods. So here are two simple ones, less than and equals. They're defined on everything that is a typed type, so we don't restrict them to numeric types, but the real Slick has different classes of extension methods for numerics and for all types and for strings and booleans and whatever. And the way these work is that you take the original rep, you take another rep, and then you build a new rep, in this case a rep of Boolean, which contains the AST to return. So that's an apply, because we have a function or operator application, and the children are n.toNode and e.toNode, the two sides of the operator. Okay, so we can write scalar computations now on primitive values and columns. What about tables? Now a table is defined through an abstract class table of t, which extends rep of t. And in the example below, you can see we have a class users, which extends table of tuple of int, string, and string. Now this is a case where just knowing that it's a rep of t is not enough anymore, because we don't just want a rep of tuple of int, string, and string. We want to be able to say u.id or u.first. So we need to keep those column names available. That means we need to know it's actually an instance of users. And we extend this table class, and we add methods to it, or we add columns to it by calling a column method. Again, it takes a type which has a typed type evidence available. So we restrict it to primitive types, and it builds a select which is based on whatever the toNode returns for the table, and then we generate a symbol with the field name. So if the table is currently tagged as S2 and you call the column ID, then you then the AST will say s2.id. So that's a select of field ID in S2. So since we need to keep the real subtype of the table, not just a rep of t, we need a way to rebuild this table instance in encoderef. Therefore, it's not enough that we just give Slick an instance of this table class. We need to give it a constructor from which Slick can build new instances of the table class. And that's what this tag is for. So what you give Slick when you want to build a table query, the original user's query that we started with, is a function from a tag to the users table. That's just the constructor of the users table. And the actual logic of encoderef and to node is implemented in the tag. So this kind of goes recursively through the table and the tag, so that whenever we call encoderef on the table, it calls encoderef on the table tag, and this calls the original constructor again. And initially we put in a tag that returns this node that we pass to toNode. So that's up here. That's a table node. So there's an intrinsic table node inside a table. But as soon as you encode some path into it, then you get the path out, just like you would for a standard rep. So we got primitive values, we got tables. Now we need tuples. So what are we going to do? Well, we start with what I started with in Scala query when I created this back in 2008, 2009, with the assumption that everything needs to be a rep of t. So we need a lifted representation for a tuple, some rep of t that stands for a tuple. So here's one example. That's a rep tuple 2. Of course, in Scala query, I had them from 2 to 22. They're auto-generated from a template. And you use this by starting with any rep value that has a typed type. So you can only put primitive values into one of these Scala query style projections. And then you call this tilde method. And this gives you a rep tuple 2, and then you call the tilde method on rep tuple 2, and it gives you a rep tuple 3, and so on. And of course, the toNode gives you a product node, as expected. tencoderef builds another rep tuple 2, also as expected. So what we can do now is something like this. We have a map call from u to u.id tilde u.first tilde u.last. That's nice and gets the job done, but it's not really what we want, because I don't want users to learn this new syntax, even though it's sort of elegant. What I want to be able to write is this. I want to use real Scala tuples here, because it's much easier to use. And why stop at Scala tuples with primitive element types in them? When I join two tables, I don't want to take all the columns apart and then put them back into one single tuple like I had to do in Scala query. I want to be able to put whole objects in there, like the users row. I'll put the whole row in there, and a u.first and a u.last. And if we can already put compound values like a table row inside of it, why not another tuple? So let's do nested tuples. And if we can do nested tuples, why stop there? Why not HLists? HLists are just nested tuples, as you learned from Daniel's talk. So what do all these things have in common, though? All these types that we see here? Well, they are not a rep of t. So we have to let go of this very basic assumption of the lifted embedding, that every value that we work with has a type that is a rep of t. What these types instead are is polymorphic record types. So now we'll define the second part of the talk's title. So what is a record type? It's a pretty common term when working with database technology. A record type has a fixed number of elements with a known type. So these are ordered or named. Usually the definition is that they have names, but when you have tuples, the tuple elements have names. They're just _1, _2, and so on. The important fact is that it's a fixed number of elements, and the types are also fixed and known. HLists kind of fall under this definition, even though they can represent values of arbitrary sizes, because the size is still determined by the concrete type. That's enough for us. And polymorphic means that they abstract over element types. The important bit here is that you can have the same record type to hold values of a primitive Scala type like int or string, and of the corresponding lifted type like rep of int and rep of string. So here are some examples of these polymorphic record types. Well, tuples, obviously. You can have a tuple of int, string, and string, and also a tuple of rep of int, rep of string, and rep of string. And you can put something like a users table row in there, as we see in the third example here. And then there are other product-like types. They don't have to be actual Scala products, just something that's isomorphic to a tuple, like this pair. That's like a tuple 2. It's the same thing, except it has a different name. And we call the values v1 and v2 instead of _1 and _2. And since we can have nested tuples, we can also allow HLists, because they are isomorphic to nested tuples. Okay, we need one basic prerequisite in order to be able to encode these polymorphic record types, and that's functional dependencies. Now, what are functional dependencies? They are dependencies between type parameters. We can use a technique to encode a function at the type level that translates from one type parameter to another. And of course, the mechanism we use for this, as usual in Scala, is implicits. So let's start with a simple implicits example. We have a function or method f with two type parameters, t1, t2. It takes a value of type t1 and returns a value of type t2. And it does that by calling a converter function. And this converter function is an object convert of t1 and t2, and it's passed implicitly. And we have three of them predefined, from int to long, from long to string, from string to int. So if you look at the example at the bottom, we have a value of type int. We put that in here, so we get t1. It's now defined. And we know that we have a long. So we know t2. We know both of these types here. So we go from int to long. There's only one match. And we put that in here, and everything compiles, right? This doesn't need functional dependencies. This is just basic implicits. Now the interesting part is I can remove all the type annotations down here, and it still compiles. That's where we need the functional dependencies for. So what happens in this case? Well, we start with an int. So that's our t1. We know t1 is an int, okay, but we do not know the result type of this computation. This is undetermined. It's just a val L, whatever this type will be eventually. So let's mark this with an underscore because we don't know it yet. We can still perform an implicit search from int to whatever, because there's only one convert instance that starts with an int. It's this one. We still find the right instance, this int to long, and we put it down here. And now the interesting part happens. The type inferencer now knows that t2 has to be long because it now has this information. So we put the long back here, and of course back here, and this is the return type. So now we know the return type is long. And this val L below is of type long. And then when we do the next conversion, we start with a long, and we have a converter from long to string, so we now know that S is a string, and finally we convert from string to int as before. The types are determined through this convert type class, and you can almost imagine these arrows here. This is a function that we've written that translates from one type to another. It translates from int to long, from long to string, and from string to int. Here's another example. CanBuildFrom in the Scala standard library. This was actually the reason for adding functional dependencies to Scala in the first place. They were added in Scala 2.8 with the collections redesign. And this gave us CanBuildFrom. What this enables is to write implementations like map very high up in the collections hierarchy. Like here we see the class is traversable-like, which is way up in the collections hierarchy. If you have something like a vector of int, then this vector extends index seek, extends seek, extends, it extends immutable index seek, it extends immutable seek, extends generic seek, extends generic traversable, extends generic traversable-like. That's pretty much how it goes. And map is already defined up there in traversable-like. Implementations can still override it further down in the hierarchy, but they don't have to. It's only for performance. But still, this map needs to build an instance of the right collection, usually the one you put in. If you have a vector and you call map on it, you want to get another vector out of that. So that's what you use CanBuildFrom for. So you can see this type A. In our vector of int example, that would be int. That's the element type. And wrapper, that's the actual subtype. So this would be vector of int. And then we look for in map, we look for a CanBuildFrom from wrapper of int and b, which is what the mapping function returns. So if you have a function from int to string, we look for a CanBuildFrom of vector of int, comma, string, comma, whatever. And this whatever is the return type. And there are implicits in the collections implementation which define these return types in a very elaborate and easy to break way. It allows some neat tricks, like when you have a bit set, which is a specialized set implementation that only works on integer values, and you have a map call on that which produces another integer, you get a bit set out of that, and it's statically typed as a bit set. If you provided a function that converts the integer to a string, you get some generic hash set out of it. And that's encoded through these functional dependencies via CanBuildFrom. So let's see how we can use that in our lifted embedding. And the type there is called shape. Every value or expression in the lifted embedding, which does no longer have to be a rep of t, now needs to have an implicit shape available. So instead of hard coding, a rep of t eventually produces a value of type t, we now say a mixed type eventually produces an unpacked type, provided there is an implicit shape from mixed to unpacked available. And the lookup is always done by this mixed type. The implicit shapes are defined uniquely by the mixed type. So when all you know is the mixed type, you can still look up the correct shape, and you will get the unpacked type and also the packed type automatically. The unpacked type is the same as in rep of t goes to t. That's just the t, what you get out when you run this thing. The packed type is basically the reverse of that. So it has reps everywhere. So if you start with an int, you go to a rep of int if you look at the packed type. We'll see why we need that a bit later. So let's start with the primitive shapes. Well, we want every value to have a shape. So for example, there's a an implicit def primitive shape, which works for any type t which is primitive. So it has a typed type. In our case, int, string, and boolean. And this gives us a shape of t, rep of t. So we start with, say, an int, and this unpacks to an int, which it already is, and it packs to a rep of int. And we also have a column shape, which is very similar because it also requires a typed type t, but it gives us a shape for a rep of t, which unpacks to a t and packs to a rep of t. And we have a table shape, which is available for every type C, which is a subtype of table. And it gives us a shape for C, which unpacks to T and packs to C. This implicit here, that's to overcome a limitation of the type inferencer. Because we need a C, which is a subtype of table of T, and this is a neat little trick to get both of them inferred correctly. So what do we do about tuples? Well, obviously we need to provide a shape for them. So we have a tuple2 shape, and again, these are generated. In the Toy Slick project, you can actually see the expanded versions, but in the real Slick, they are generated by a free marker template. So tuple2 shape gives us a shape for a tuple. Let's see how this is used in implicit search. Above here you see an example of a map call, and map requires an implicit shape for the return type. So in this case it's equivalent to saying implicitly of shape of tuple of rep of string and int, and the other two types are undetermined. So we know that we need a shape for a tuple2, and we get this from tuple2 shape. Right? This is the tuple2. And then tuple2 shape says, I can only give you a shape for a tuple2 of m1 and m2 if you already have a shape for m1 and a shape for m2. So m1 is rep of string, so we have to go to column shape and look this up, because this gives us a shape for rep of string. And for m2, we have to go to primitive shape, which gives us a shape of int. And because of functional dependencies, the unpacked and packed types flow back up in this implicit search. So we now know these types here and these types, and they flow back up and back up. So we can now determine the unpacked and packed types for the whole shape. It's done in a recursive way. So this also means, of course, that if you have nested tuples, it just works automatically. You have a recursive definition. As long as you have a shape for something, it works, even if that nested shape is again a tuple shape. So here we have a tuple2, which is this thing. So we need a tuple2 shape. And then the first side is a rep of string, the second one is another tuple2. And of course that means we go back to tuple2 shape. And again, when you go down in the implicit search, you take the mixed types apart and find shapes for them, which determine the unpacked and the packed types, and they all flow back up in the implicit search recursively. Okay, that's for the types. Now what do we do about the implementation? Well, since shapes are supposed to replace the requirement of having a rep of t, they need to do kind of the same thing. So a shape needs a toNode and an encoderef implementation. Of course, for a shape, these two now take values too, because a shape does not represent a specific value, it only represents a type. So we now need to combine it with the value, which is an instance of the mixed type. And then we have two methods, pack and packed shape. So pack takes an instance of the mixed type and produces the packed type, and packed shape gives us the matching shape for that. Again, we'll see why we need that a bit later. Here's the most straightforward shape implementation. That's rep shape. We use that for anything that used to be a rep of t and now needs a shape, like the implicit column shape and the implicit table shape. They both just delegate to rep shape. Now, what rep shape requires is that we have a type which is both the mixed and the packed type, and this must be a rep type. And then we can get a shape of mp, u, mp, and of course, to node and encode ref just delegate to the matching methods in the rep, and packed shape are identity operations because the shape is already packed. The mixed and packed type are the same. For primitive shape, we need a different implementation. If we have a primitive value like 42, we need a shape for that. So we want a shape with a mixed type t, and if we pack that, we get a literal rep because we need a rep of t. So we use the literal rep, and the packed shape is of course the rep shape for that because it's a rep. The to-node, we go the easy route there by just packing it and calling to-node on the packed version because that has to be the same. But encode ref, unfortunately, is a bit of a problem. We have to throw an exception. Because if you remember the invariant from rep of t, if you encode a path with encode ref and then call to-node, it has to return that path. But this value v here, this could be an int or a string. You can't encode anything into an int or a string. There's just no way to implement encode ref, so we have to throw an exception. And this will probably create a problem later on. So let's move on to queries. We haven't looked at collection valued stuff at all. We've only dealt with scalar computations so far. For queries, which should really be called views because anything can be a query, but here's query specifically means a collection valued query. So a query is a rep of seek of u. It's collection valued. And the query takes two type parameters. E is the so-called mixed type from the shape, and u is the unpacked type. We encode both of them in the query to work around a limitation that Scala once had. We could probably get rid of that in Scala 2.11 and higher. So the to-node is just a node that we pass in, and we also have a shaped value. That's just a shape plus its value combined for convenience. And again, you see the two types here. It's the element type or mixed type and the unpacked type that you get when you run this query. Encode ref just returns a new query with the new path and the old shaped value. And we want to create an initial query from a table, so that's what table query does. We give it a class that subclasses table and the constructor for that, and it gives us a query for this table, which just calls to node, so we get the table node out of it initially. That's what we've seen in the AST. So how do we implement some methods on this, some operations? We only have two operations in ToySlick that are defined in queries, and that's map and filter. Otherwise, there wouldn't be any interesting examples to write without at least map and filter. So the simple one is filter. Usually on a collection, a filter method takes a function from E to Boolean, from the element type to Boolean. Since we're in the lifted embedding here, we take a function from E to rep of Boolean instead. We don't need a shape here. We can say rep of Boolean because for primitive values we can always assume a rep. Otherwise, a literal can just be converted. That's okay. And from a query of E, u, this produces another query of E, u. It doesn't change the type. So how do we implement it? Well, we know that we want a type and that we want an expression that acts, we want a symbol, an expression that acts on this symbol. So we create a fresh symbol. That's the S9 in our example here. And then we encode this symbol as a ref to the symbol. We encode this into the shaped value, call the user's applied function on it, and that gives us a new value that can produce the node for this where condition. The query gets a filter node, so we eventually get the filter out in the AST. We see the symbol. This is this one here. The from clause is toNode, so that's the table query. And then this is the where condition, which references S9 because we encoded that into the original value here. So that's how filter works. And if we look at map, it's actually quite similar. This is a naive implementation of map, which still has one small problem, but the basics are similar to filter. So we take a function from E to F. In this case, the F could be anything, so we really need a shape for that. So we need a shape of F, and we also need a new unpacked type T, and we return a query of F and T. Again, we create a fresh symbol, which goes down here. We put the original toNode in here for the table users. We encode the ref into the original shaped value. We call the user's applied function, but now the return type, the return value of this user's applied function, that's what we have to put into the new query. This determines a new type and a new shaped value, which is our prototype value that we need to keep around. So we pack those up as a shaped value. Fv is the computed value, and shape is the shape we got for it. And we put that into the new query. So far, so good. And our example works perfectly. We can write a map that takes a u and maps that to a tuple of u.first and 42. So where's the problem with this? Well, look at this slightly more complicated example. We have one map call that maps the user's row u to tuple of u.first, 42, and another map call which just takes this tuple 2 that we produced and maps it to its first part and its second part. I could also have written map identity. It's the same thing as far as Slick is concerned, because we only see the paths in the individual elements. But where's the problem here? Well, this thing is an int, right? It's not a rep of int, it's an int. So this would also have to be an int. And in order to run map, we have to take our shaped value and encode the path into it. So we call encode ref, and we're back in primitive shape, and it blows up because we cannot encode the ref into an int value. And that's what we need the packed type for. We could encode it into a rep of int, which is the packed type of int. So that's what we're going to do. In the real map implementation, we'll also collect the packed type, but we'll call it G. And instead of returning a query of f, t, we'll return a query of g, t, the packed type. And we get the value by just calling packed value on the shape value. So now if we run this, we get a rep of int. So every collection operation that produces some new values inside, like map or flat map, has to pack the result in the end so that you can use it to encode something else into this result. This also gives us a more precise definition for what this packed type is. Previously, I have called it a type that has reps everywhere. What we actually mean by this, it has to be a type that whose shape supports encoderef, so that we encode a path into it. So I don't want to go into the details of the tuple shape implementations. There's a ton of superclasses here, like product node shape, which make this easier, and we have a tuple shape which extends that, and so on. I just want to show you the principle of how the encoding works at the value level by looking at this toNode and encoderef. So in the case of toNode, we take the shapes, which are the shapes of the child elements, and we zip it with the actual element values, and then we call toNode pairwise on those and put the result into a product node. So it just zips the original implementations of the individual values. And the same goes for encoderef. We take the element shapes, we take the element values, and we take the index of them and zip all of that up. And then we call encoderef on these individual values. And what we encode is a path, a select that selects a symbol underscore plus position plus 1. So when you say x dot underscore 1 on a tuple x, it will actually encode this as a symbol x, as a select of x dot underscore 1 in the AST. And then build value will build the tuple. That's a generated utility function, because we also need 22 of those again, because we have to support the tuples for each arity separately. So finally, let's get to heterogeneous lists, or HLists. Most of you have probably seen Daniel's talks, so you already know what HLists are. I'll just keep it simple here. We have an abstract class HList, and we have an object HNil, and a class HCons. So that's like a standard Scala list, which has a nil object and a cons class to concatenate elements at the beginning of the list. The difference is that in an HList, you also do the concatenation in the types, not just the values. So you can have a type like hcons of int, comma, hcons of string, comma, hnil.type. And with some syntactic sugar on top, we can write that type as int colon colon string colon colon hnil. So the same as in the value domain. But these are just like nested tuples. They have a recursive definition here. We have an hnil as the base case, and we have an hcons as the recursive case. So this means we should be able to do the same with the shapes, right? And in fact, we can. This is all you need. I mean, there's a superclass here that we're using, which does some of the magic, but the actual HList shape implementation is all that you see on this slide. It's complete. So the implementation appears not very interesting. The interesting part happens in the implicit. We have one implicit HNil shape for the base case. This gives us an HList shape. Oops. Gives us an HList shape for HNil, which unpacks to HNil, of course, and has no elements. And then we have an hcons shape, which gives us an HList shape for M1 concatenated to M2, provided that we have a shape for M1, whatever it is, and an HList shape for M2. We can narrow down the search space here by requiring an HList shape, because it can't be anything else, and so we don't need to have the compiler search for other shapes. And that's it. It's a recursive definition, and the shapes are looked up recursively, and the type inference flows recursively, first down, then up, and voila, you can use HList shapes, or you can use HLists everywhere in Slick automatically. So we have a class users for the table row, which has this HList type here. We use HLists for the star projection, and we write an expression here which also uses an HList. Well, that's as much as I have. we made it to the HList. So here are some links, of course, for the regular Slick, slick.lightbend.com, and also the link to the toy Slick. If you want to play with this, you can just clone it from GitHub and do spt run and look at the source code. It's just a few files left from the original Slick. And you can follow me on Twitter if you like, or ask questions if you have any. Thanks. No questions? There's one.
What are the major sources of additional complication in the real Slick?
The biggest one is options, because I've simplified it here to requiring a typed type for any primitive type. We have to distinguish there between a base typed type and an option typed type, and then we need to set up shapes for those. And that was the simple part. That's what we had before Slick 3.1, I think, or 3.0. And then we added options of complex types, like for outer joins. When you have a left-hand side and a right-hand side, and you do a regular join, you get a seek of like T1 and T2. But if you do a left outer join, you get a seek of option of T1 and T2. That's the correct type, even if T1 is a compound type. And it turns out that the right type for these option types is different from the type that we use for primitive options. So essentially the correct type for option would be rep of option of rep of int. But what we had for primitives is rep of option of int. And reconciling those was a big amount of work, actually, and led to some complications. Well, great then. Thank you for attending the talk.